So now today we will learn about windkessel effects, influence on elastic walls. As an example, I took here. All the analysis of the preceding sections is based on the premise that the fluid flows in a rigid walled vessel. Blood vessels in the body are particularly the large arteries are elastic. So we shall start with the windkessel theory. The first theory of the flow is in the aorta, as we are seeing here, was developed by Frank in 1899. It was assumed that the aorta acts on an elastic reservoir. Its instantaneous volume and pressure are related by an equilibrium equation, and the rate of outflow is determined by the peripheral resistance. This elastic recoil to the diastolic distension diameter is called the Windkessel effect. This is often due to the collagen and elastic content. No energy is required to return the elastic flow, the regurgitation. This is a working model of how the change in volume of an elastic walled vessel of radius r, thickness t, and Young's module E under the action of an internal pressure P can be calculated by consideration of an equilibrium of the wall tube. So this is the working model, how the blood regurgitation and flow takes from the left artery, from the left side of the heart, where the AV and SA node are working with the Purkinje's fiber, and then the change in the volume is approximately proportional to the applied pressure. Now we are seeing the formula for the Quadrivius equation. Here the initial condition was rather special, and let's consider the more general initial condition. If we take the y ratio 0 and x would be somewhere around the n, so here would be n multiplied by n plus 1 upon cos s square x. Here the x is the equation of x here, as shown is 0 0.2, 0 0.4, 0 0.6, 0 0.8, 1.1. So if we take the n value 0 0.5, then somehow the ratio in the x to the y comes like this here. And now if we take n to the power and the value of n1, then it somehow replicates to 2 on the y-axis. On x-axis it remains on minus 10 to minus 5. You see here for n equals to minus n equals to 1.5. This propagation of the pressure pulse, the Korteweg equation, a simple model describing the flow of an inviscid fluid in an elastic tube, can be developed by consideration of the continuity and momentum equations. The fluid is homogeneous and isotropic. The fun begins when the two solitons meet, and we saw already in the video of solitons in the lab, as I show further before. The two solitons emerge from the collision with the same species and velocities. When they start in the initial, they are of same length, but after superposition, they change their shape. They changes their shape by changing the power. The two solitons emerged here. If we see on the ratio of y to the x, then it looks somehow like this. Now finally, when the scientists took this equation calculation to the computer, and then the graph emerged like this, where the solitons are taking place of each other, you can see. So this is the working model on which the Scott Russell noticed many of the unusual properties of solitons, and we conveys this observation till today's date. So thank you.